Algorithmic thinking. What is an algorithm and why are they so important? The aim of this course is to get us comfortable with writing code. Before we do that, it's worth taking a little time to illustrate the kind of logic we want to be using when going from some problem space to some potential solution, to a working implementation of that solution. For this, we want to practice algorithmic thinking. That is, breaking down the solution to a problem into an objective set of instructions. Instructions that could, in theory, be followed by anyone, anywhere. A bit like a cooking recipe, or assembly instructions for a piece of furniture. In computer studies, we call this kind of sequential, finite, and definite set of instructions an algorithm, which we can use to write a solution in the form of a program. To start this course, we'll spend some time focusing on the algorithm part before we look at writing programs, which will be the majority of the course. The reason algorithms are so important is that they are context and platform independent and are flexible in the way they're written, so long as they are interpretable and correct. Compare this to programming. When working with a programming language, that language will have its own rules as to exactly how things need to be written, called its syntax. Whoever is writing the program needs to understand and follow these rules, otherwise the program simply will not run. Algorithms, on the other hand, are a lot more forgiving. Your algorithm still needs to make sense, and still needs to accomplish whatever it is you're trying to do, but beyond that, you can kind of write it however you want, as a flowchart, step-by-step instructions, or even just written in plain text, in whichever language you want. Writing an algorithm. We're now going to practice taking a problem and developing a solution using an algorithm with a very simple everyday example. The problem is wanting a cup of tea. Our output will be a cup of tea. For this example, this problem space, we'll say we have a kettle, a box of tea bags, a mug, etc. But for some reason, we, or whoever it is who's going to be making our tea, doesn't know what to do with them. What we would do is write out step-by-step instructions for making tea such that they can be followed by anyone. We're going to write this as a fake program. This style is called pseudocode. It gives us the structure and definition and overall feel of code without the risk that something could go wrong if we make a minor grammatical mistake. Maybe this looks a little strange, and that's okay. This is basically pretend code, not for a real programming language, and as such, the exact wording and structure is not important so long as it's interpretable. Algorithms are completely scalable for as much or as little detail as you need them, depending on the context of the problem. Here, we've made the assumption that whoever or whatever can interpret the individual instructions like kettle.fill or put mug teabag. But if we needed to, or wanted to, we can break those instructions down even further. Take kettle off stand, take kettle to tap, turn on tap, etc. On the other hand, if making tea was just one step of a larger algorithm, say making breakfast, and we knew whoever we were writing it for knew how to make tea, we could condense it down to just one line. It depends on what we already have, what we assume we know, and what we need. That is what we mean by problem space. Bubble sort. Making tea is a good example to start with when it comes to making step-by-step algorithms, but it's unlikely to be the kind of program we'll be writing code for anytime soon. Let's look at a similarly simple but more abstract, more computery example, the kind we very much could be writing code for: sorting a list of numbers. Let's break down the problem space here. We have a list of numbers. We can move numbers around the list. We can compare numbers by size. We can't add, change, or remove numbers from the list. And we want the list to be in order, smallest to largest. We're going to take a look at a famous solution to the problem, the bubble sort algorithm. We'll be talking through this algorithm in just everyday speech, which, remember, is really all we need, and then taking a brief look at some other perhaps more formal ways of it being written out. Bubble sort starts like this. Compare the first and second elements, that is, numbers, in the list. 1 and 17. Are they in the right order? In this case they are, so we move on. Next, we compare the second and third elements in the list, so 17 and 3. Again, we ask, are they in the right order? In a sorted list, we'd expect 3 to come before 17, so they cannot be in the correct order here. What we do is reverse the order of just these two numbers before moving on. Next, we compare the third and fourth elements of the list as it exists now. Remember, we just swapped those last two numbers. Here, we're comparing 17 and 16. Again, we'd expect 16 to come before 17, so we swap them around. And we move on to the fourth and fifth, then the fifth and sixth, then the sixth and seventh, and so on until we reach the end of the list with the second to last and last elements. Although, even after one pass, this isn't a fully sorted list. So we go again. And we keep repeating until we manage one full pass of the list without changing any numbers. We know that if we can do this, that is, if no numbers in the list come before any numbers that are smaller than themselves, then the list must be sorted. This algorithm can be applied to any list of any length with any different numbers in it. It will always work, whether we only need to swap two numbers, whether it would take hundreds of cycles, or even if it was in the correct order to begin with. It will always end up with a perfectly sorted list. And that is bubble sort, so called because the numbers rise or bubble up through the list into the correct position over time. We can represent this same algorithm in several different ways. Pseudocode, flowchart, step-by-step, and also worth noting is that this is far from the only way to order a list. That is, there are multiple correct algorithms for this problem space. In fact, bubble sort is actually one of the slowest ways of doing it. So, that's it. We know what an algorithm is. Ideally, we should always have some idea of what algorithm, that is, what step-by-step solution we want to implement after looking at a problem, but before we even write our first line of code. With this in mind, you're ready to learn to code.